Okay, so problem 4 is very similar to the previous problems, except now you have an applied moment. And you're trying to find the value of the moment required at A to make the rotation at A 0. So again, this is working with moments tends to throw a lot of people off as opposed to working with regular forces, but it's really not too bad. I think it's just the graphs will look different than what you're normally used to, so that's what tends to throw people off. But just do your normal process. Let's call this our P system here. So this is my P system. Find the axial forces. Sorry, I lied. There's no area information given. It doesn't say to leave it in terms of A. It doesn't tell you what the cross-sectional area of these members are. So you can ignore axial deformations. So in other words, just draw the moment diagram for this problem. Right? Just draw the moment diagram for this problem. The next step, you want to find the horizontal deflection at D. Therefore, your Q system, right, is you're just gonna apply unit load of 1. And you want to find the rotation at A. To find horizontal displacement, I applied a unit force. To find rotation at a point, I'm going to apply a unit moment. This is my Q for delta D. This is my Q for theta A. Okay, once I have my moment diagram for my P system, my moment diagram for my Q1 system, my moment diagram for my Q2 system, I'm going to go back to my table. I'm going to match the shapes. So for example, if my Q system, I think in this case my P and Q systems would both be triangles. So again, I would use this one. I'd end up with a triangle and a triangle for my Q1 system. I would use this 1/3. This is what I think. I didn't actually do this yet, so you'll have to double check. But I think I would end up using my 1/3 M1, M3 on L, all on EI. I would multiply that out for this term. Do the same thing again for the top term. Notice that the top one is 2i. So you'll have an extra factor of 2 in the denominator here. And that will be plus something, something. That'll give me my deflection at C. Is that point C? Point D rather. Point D in the x direction. I would solve this one using the same procedure. Once I have my moment diagram, I match shapes and I match values. I plug those values into my formula. I'll have 2 arms. So again, I'll have 2 arms here. I'll have 2 terms here. That'll equal my delta theta. And once I have that, the final part is asking me to find the force P here that gives me 0 rotation. I already have this as a Q system, right? So I just take this. So this would be an applied moment, or this would be N. I need to find some force N to apply here, some moment N to apply here that'll give me 0 rotation a day. I already have a Q system like this, right? These two are very similar. They're just off by a factor of N. So I'm going to multiply all the results I got in here by N. And that'll give me my, I'll do the same thing that I had before. This is delta theta due to N. I'm gonna set my, let's call this 1, 2, delta theta 1 plus delta theta 2 is equal to 0. Solve for n. Okey-doke. And I had the same feeling that I probably lost quite a few of you. I think that after you do a couple more examples, I think the professor will be doing a lot of examples of this on Tuesday. So after he does a couple more examples, I think this P system and Q system will make a little bit more sense. Once you do this a couple times, it all gets easier, but the first couple times it is a little bit tricky. So if you have any questions on this, feel free to stop by and see one of us, and we'll try to help you out as best we can. So yeah, let us know if you have any questions.